My name's Darren Holmes, and you may have noticed that ABRA has modified its Learn How to Solder kit. So the kit still includes a soldering iron, a tube of solder, a solder stand, a pair of side cutters, some perf board to practice soldering resistors and ICs onto. So to this kit I still have to add a desoldering pump, a set of needle nose pliers, and some desolder braid. So originally these kits came with the ABRA LED flasher kit, but now they include the ABRA AK 75 LED ripple kit. I just wanted to show you the solder kit on ABRA's website, and if you click on the description tab and scroll down, it tells you what the contents of the kit is. If you click on the Attachments tab and scroll down, it shows you each of the manuals that we'll be using in this video. Also on ABRA's website is the AK 75 kit, and if you scroll down to the description, you can say you can hack this board to create a Knight Rider circuit. They don't give you any information on that in the attachments, but in this video I will show you how to accomplish this. So you'll notice the cover of the Learn How to Solder Kit manual now includes a picture of the AK 75 LED ripple kit. It still gives you exercise 1 on the BRD 120, where we solder in the individual resistors, and exercise 2, where we're soldering BRD 140, where we're going to solder a couple of ICs onto the smaller piece of perf board. Exercise number 3 has changed slightly, so it now references the AK 75 LED ripple kit. I just want to remind you, over on my YouTube channel, under Projects for Electronic Fabrication, project number 2, part 1, is ABRA Learn How to Solder Kit. And in this video, I show you how to solder in the resistors and the ICs into the perf board. So you should watch this video before you continue on building any more projects. Now over the last couple of years, ABRA's been modifying their AK 75 ripple kits. So they're basically the same kit, but you'll notice the photo on the front of the package has changed slightly. So each of these kits has a slightly different printed circuit board, which means they have a slightly different layout. All of these circuit boards use the 555 timer to generate a pulse, and each of the circuit boards uses the 4017 1 of 10 ripple counters. So on each of these boards, the reference numbers that they put down here are going to be different. But we can see this is where the LEDs go along the top edge of the board, followed by their current limiting resistors. Now they've decided to use 1K ohm resistors. There's a 50K ohm potentiometer and 2 capacitors, so C1 and C2. And you can see C2 is an electrolytic capacitor, and they're saying it's going to be 1 microfarad. For the timing of the 555 timer, R1 is 47K and R2 is 2.2K. Now in later versions of this board, they went with 2.2K and 10K. So 47K might be a little bit large. We'll have to do the calculations and find out how slow this will make the board go. And like I said, in the latest version, they actually use 10K instead of 47K. So on the next version of the board, you can see they tried to make it not quite as long as the first edition. They've done that by taking the individual current limiting resistors to the LEDs and moving them up, and a couple of them are actually positioned horizontally. You can tell this board from the most current version of the board by the silk screening for the 50K ohm potentiometer. On the latest board, the silk screening is more of a roundish shape. Now with this particular board, they started including a schematic in the parts kit. So in this version of the kit, they've included a schematic And you'll notice that there is actually C1, C2, and C3. Now C2 is used on the control voltage line to ground. Most of the time we can omit this particular capacitor. You'll notice it goes between pin 5 and pin 1. So if you take a look at the silk screening on this board, we can locate C1 and we can locate C3, and we have no clue where C2 has disappeared to. So if you flip the board over and take a look at the pins for the 555, you can see that pin 1 is the square pin, and it has a little trace coming off the edge here. So this is pin 1, 2, 3, 4, and pin 5. And we said the capacitor is connected between pin 5 and pin 1. And pin 5 has a little trace coming off of it. So it looks like when they developed this board, they had no way to run the traces so that they could run it up here and put a capacitor in here. So they've actually left off C2. So checking the actual parts list, you can see C1 and C3, and there is no reference to C2. The circuit's going to run just fine without C2. So this is the newest version of their printed circuit board. You can see the silk screening for the 50k ohm potentiometer is more round in shape. And when we're looking for the capacitors, we can see there's C1 and C2, and there is no reference to C3. And when we take a look at the bottom of the board, specifically around the 555 timer, you can see that pin 1 no longer has that little piece of trace sticking out, and pin 5 has no trace going to it. They've also included a small schematic in the parts kit, and you can see off of pin 5 they're not even drawing in that little capacitor anymore. You can see C1 and C2 are both 1 microfarad capacitors, and they can both be electrolytic capacitors. So included with that little schematic is a parts list. There's a lot of Chinese writing here, but we can see R1 through R10. There's 10 of these resistors, and they're 1k ohm. R11 is a 2.2k ohm resistor. R13 is our 50k ohm potentiometer. D1 through D10, that's 10 LEDs. You'll note there's 2 U1s here. The first U1 references the 555 timer IC. The second one represents that 8-pin socket that the timer IC plugs into. R12 is going to be a 10k ohm resistor. C1 and C2, they're 2 1 microfarad capacitors. They're going to be cans, so they're electrolytic. There's 2 U2s. The first one references the CD4017 IC. The second one represents the 16-pin socket. J1 is a 2-terminal connector, and they have 1 printed circuit board. Now the kits come with a full color instruction page, so they actually show you what the LEDs look like, the positive and negative, or anode and cathode, and they're saying the positive leg is the longer leg. They're showing you the capacitor here, and you can see it's a polarized capacitor. So once again, the shorter leg goes to the negative side, the longer leg is the positive. And here they're showing you what the 555 timer looks like, and it says look for the dent that is always the front. And remember, this will be pin 1. Pin 1 is always to the left of the top. So it goes pin 1, 2, 3, 4, and 5 is on the other side, 6, 7, 8. So down here on the bottom, you can see they give you the color codes for resistors. They tell you what each of these resistors is and the color codes to expect. And they also give you a pinout for the 555 and the 4017. So on the back of the page, they give you another copy of the schematic as well as a photo of what the board should look like. So if some of your silk screening is worn off, you can actually use this as a reference. The first thing you need to do is identify all your components. So the first component is a 1K ohm resistor. There's 10 of them, so they should be in a strip of 10. The next component is a 2.2K ohm resistor. So that's 2,200 ohms. So the color band should be 2, 2, and we need 2 more zeros after that. So when you look at the color bands, they're not the standard 4 color bands. They could be the 5 or 6 color bands. So in my case, my resistor is red, which stands for 2, red, that stands for 2, black, which is 0, followed by a multiplier of brown, which is 1. So the resistor is 2, 2, followed by 2 zeros. So that's 2.2K ohms. The other resistor is the 10K ohm resistor. So I just want to remind you, in your instructions they do show you the color band reference chart, and in here they have 4 band, 5 band, and 6 bands. And you can see they give you an example at the bottom here of brown, black, black, red, brown. And they translate that out for you, and that is your 10K ohm resistor. And I just want to remind you, if you're not sure about those resistor color bands, you can always use the ohm meter to check. So here you can see my 2.2K ohm resistor is measuring at 2.164 kilo ohms. The next item down is the 50K potentiometer, and you'll notice it's labeled 503. So that's 50 with 3 more zeros after it, so that's 50K. The next item is the LED, and you'll notice it has a short leg and a long leg, so the long leg is the positive leg. There's 10 of them in your kit. I actually had 11 in my kit. Next item down is the NE555. So when you look at my IC, you can see there's a little smile at the top, or a little dent. So that means immediately to the left is pin 1. Below that is an 8 IC. That's the socket that the chip actually fits into. Please notice it has a little dent at the top here. So this is pin 1 on this side. It's important to place these in the correct way on your printed circuit board, because then you come along and put your IC in and orient it the same way as the socket. Over here we have 2 capacitors. It'll be labeled right on them. 1 microfarad. There'll be a long leg and a short leg, and on the short leg side there should be a white stripe down the side of it saying that's the negative side. Next item down is the 4017, and it's a 16-pin IC, so it needs a 16-pin socket. So that's the next item. Please note that there is a little dent at the top again, and immediately to the left is pin 1. Then there's a J1. This is a screw terminal, and we can put some wires in it to power up our board. And lastly, we have our printed circuit board. So the next thing we want to do is check to make sure our printed circuit board was okay. So what we're going to do is use our digital multimeter and put it onto the ohms setting. Now remember, at infinite ohms, it's just going to flash 40. Now what we'd like to do is to be able to just test it without looking at our meter. So what we want to do is put our 2 banana leads together, and you'll notice that the meter is reading approximately 0 ohms. It'd be nice to be able to know what that is without having to look up at the meter. So if we press the blue button, it will put it in beep mode. And when we separate our banana leads, there's no beep, and when they touch, it indicates 0 ohms. So taking our 2 banana leads, we're going to check the traces on the board. Now in my last video on the blinking light, one of the traces was not connected to the pad. And that can happen occasionally. So all you have to do is take one lead, and it doesn't matter if it's the black lead or the red lead, and just place it on one pad and hold it there. Then with the other banana lead, just follow the trace along until you find another pad, and then touch it. So when it beeps, it means it's connected. So just follow it around to the next place it goes, and continue on following it until you've checked everywhere that trace goes, just to make sure that all the pads are connected to that trace. Then you can check the next pad and follow it along the trace and make sure that it connects to all those pads. So once you've checked all the traces, make it to all the pads, we now want to check and make sure that the traces do not connect to each other. So for instance, this big pad here should not connect to this big pad here. So if I put one lead on one pad and the other lead on the other pad, it should not beep. So what we're doing is we're checking traces that run by each other. So we can see that this trace here and the trace underneath it are close together. So we just want to check between two pins and make sure that there is no physical connection. Because sometimes when they etch these boards, it doesn't actually oxidize all the copper off between the traces, and sometimes you can be left with little shorts here. And when you get these little shorts, all you need to do is come along with a screwdriver or an X-Acto knife and just scrape between the traces where they make contact. It's just one more step you can do to ensure that your board is working. Now when they actually make large boards for computers, they actually have a machine that goes along and checks all the individual pads and makes sure that they don't short to other pads and they do connect along the trace lines. But for small run boards like this, they're not usually checked at the factory. So the next thing I like students to do is to engrave their name on the board so that they don't lose it or pick up somebody else's by mistake. This is a Dremel Model 290. It has the on-off switch on the back plate here. And it also has a dial-in gauge here, so you can select how deep it goes. I like to put it about halfway, so somewhere around 3 on a scale of 1 to 5. And remember, the harder that you push, the deeper into the board it's going to go. So try it on a little blank area first before you try it out. So on the board, you're trying to find a blank space where you can put your name. If you look at the bottom of the board where all the pads and traces are, you can see there's not too much room to put anything on there. But if you look at the top of the board with the silk screening, right along the edge here seems to be some room for you to put your name in. So when I turn this on, it's going to be a little bit noisy. So here you can see I've just etched my last name onto the board, and it just makes it easier to identify this board as belonging to me. So once you've engraved your name on the board, the next thing I like students to do is to show me that they know how to put in some polarized components. So when you look at some of these components like the LED and the capacitor, there's a long leg and a short leg. When you're looking at IC sockets, there's a little dent at the top, so we need to match that up with the little dent that's showing on the silk screen on the printed circuit board. Sometimes students have trouble putting in potentiometers, so I like to see those go in. And we have on here a connector, and I like students to show me they know which way around it goes. It goes so that the wires go in from the outside, not the wires going in from the inside. So when looking at the silk screen on the printed circuit board, you can see the screening for the LED actually has a little plus sign on the top. So that's where the long leg goes in. So there's our LED. Make sure that the long leg goes in the top, and it should just slide in like that. When we solder our components in, we like the component to be flat to the board so that the solder on the other end doesn't just make an electrical connection, it also makes a mechanical connection. So if your LED is only soldered in maybe halfway, if you start wiggling it, it's going to break the solder off of the pad and break the pad off the traces. So that's why when we put the components in, we want them to be flush with the printed circuit board. So when you're looking at the sockets, remember we're looking for that little notch on the top of the socket to match the little notch on the printed circuit board silk screen. So be very careful when you push these in. Don't use a lot of force. Just kind of wiggle it a little bit, because if you don't get the pins lined up with the holes, if you use a lot of force, you're just going to end up bending the pins underneath the board. Same thing with the 555 timer. That has to go in. And keep in mind, right, the notch on the socket has to match the notch on the silk screen. Now you'll notice these little potentiometers have fairly long leads on them, so the leads on these don't go all the way through the board. So because they've got that little bend in the bottom of them, sometimes they have trouble. So you can see with this particular potentiometer, it's going to stand a little bit off the board. There's nothing we can do about it. These wide tabs on here will not go through the holes for the printed circuit board. Capacitors, they have a long lead and a short lead if they are polarized. So there's a long negative down the side of the can. So you notice on the silk screen, on the bottom here I have a little plus sign, on the top it's all white. So make sure you orient your capacitor in the right way around. And we have a second capacitor, and it's oriented the opposite to the first capacitor. So the long leg goes on the top. And then finally, this screw terminal connector. You notice it's got little screws on the top, and on the back there's no holes. So you want the back facing into the board. So usually I like the students to show me that they know which way around all these components go before they start soldering them into place. So now we're going to start soldering the components to the board. So I like to start with the smallest or flattest component first. So in this case it's going to be the resistors. We have 10 1K resistors to solder into place, a 2.2 and a 10K. So I'm going to start with the 2.2K ohm resistor. And we're going to orient it so that we can read it from left to right. So it's just like the silk screen on the board. So we want the red, black, brown. So the red has to go to the left side. So all we're going to do is take our resistor and bend the lead right at the case on either side. And then we just slide it into the holes that are provided for us where it says 2.2K ohms. Now because this is the flattest one on the board, I can turn my board over and the bench that it's resting on will hold it in place. So in order to solder this, I'm going to use my soldering iron that I have sitting on my bench. I'm going to wipe the tip on the sponge. I'm going to come in and I'm going to add a little bit of solder to the end of my tip. Now the reason we do that is because it aids in heat transfer. So what I want to do is I want to hold my board and I want these pins to be straight up. So the first one's kind of tricky, so I bring the tip in and I want to warm up the lead, and then I want to warm up the pad, and then I'm going to bring my solder in on the other side, and it should just melt, and then I should be able to run my tip up the lead and the solder should follow it. Now you can see in this point here the solder did not go all the way around. So I can come back here and I can reheat the pin and the pad, and I can add some more solder. And then I can run the tip up the lead, and this time you can see the solder is all the way around it. Now if you haven't got the leads perpendicular to the board, you can reheat it and then try again. Now you can see I'm holding the other lead because the first lead that I'm soldering will be very hot when you solder it. So looking at a close-up here, you can see the solder's gone all the way around the pad. It's connecting the pad to the pin, and there's no holes in the solder. And it's fairly shiny, so this is what you're trying to aim for. So normally what I do is I have the students go ahead and solder in maybe 5 or 6 components, then bring it up to me so I can give them some feedback. So if they're doing anything wrong, I like to give them some feedback because I like everybody to get a good grade in this course. Okay, so I've gone ahead and soldered the second pin in, and you want to make sure that you check back to the top of the board and make sure that the resistor is touching your board. If it's not touching the board, then you have to reheat the pad and try and press it down with your fingernail, and then hold it in place while it cools, and this can get a little tricky and a little bit hot. So the next thing we're going to need to do is actually trim these leads. So you don't want to trim it too high, and you don't want to trim it into the solder. So maybe 1/8 of an inch just above that cone is probably about where you want to trim it to. Now keep in mind that when you trim it, you want to put your hand over it so that that piece does not fly across the room and get stuck in somebody's eye. So if everybody's wearing safety glasses and you forget, it shouldn't be an issue, but you can never rely on everybody to be wearing their safety glasses. Now when you cut the second one, you want to cut it at exactly the same height. We're looking for consistency when we trim our leads, so we want all the leads to be trimmed to approximately the same height. So I'm going to go ahead now and solder in the rest of my resistors. Keep in mind that I like to see a student's work after they've soldered in a few components so that I can give them some feedback on their soldering. So keep in mind, all the resistors need to read from left to right, and when you're putting in the resistors this way, right, they also need to read from left to right, just like the silk screening on your printed circuit board. So I just want to remind you that when you're soldering these in place, don't forget to clean off your soldering iron between every solder joint that you make. You want a nice clean tip. You don't want any black material getting into your solder joints. And do the resistors one at a time. A lot of times I have students try to put all the resistors in at once, solder them all into place, then they trim them, and when they come back to the top of the board, they're all at different heights. You want to make sure that all the resistors are flat to the board. So the next component we're going to solder in is the IC sockets, and we use the IC sockets for a couple of reasons. Number one is the amount of heat that we're using could damage the ICs. So putting a socket in first, then we can put the IC in when the socket's cool. The other thing is, if some of these ICs do get damaged because you've wired something up wrong, it's easier to slide them out of the socket and try another IC in there that might be working. So make sure that you do get the little notch oriented the correct way around, and make sure that the pins line up with all the holes. When you turn the board over, you should see a pin sticking up for each hole. So a lot of times I will get students coming up to me saying their project doesn't work, and I look underneath and I see a little dome of solder and I don't see a pin sticking through it. So what's happened is, as they've tried to insert it, the pin got caught, and it got caught underneath the socket, between the socket and the board, and it doesn't come through. and then what the student does is they just kind of put a little blob of solder on the top, and it looks like it's soldered in, but if you can't feel the little pin sticking above the solder, then the pin didn't go through and it doesn't make an electrical connection. So it's very important you get all the pins in through all the holes. So make sure you double check those. So once again, we're going to hold the board flush and the socket should be able to stay in place. So what I'm going to do is I'm just going to solder the first pin in first. So you can see the first pin goes to a square pad. So I'm just going to come in here and solder this one into place first. Now once you've soldered the first pin into place, turn the board over and make sure that it is flush. So you might need to turn it from several angles, and you might need to press on one side with your finger and reheat that pin and just push the socket so that it is flush with the board. So once you're happy with it, then you can go ahead and solder in all the other pins. Now I've soldered the first pin in. I don't like to solder the second pin in because it's directly close to the first pin that I've soldered in. And if you get too much heat building up between the pins, you could melt the socket because the socket's only plastic. So what I like to do is go through here and solder every other pin. So I've done the first, so now I'm going to do the third. So then when you're happy with that, you can come over here to the other side and continue doing every other pin. And then you can come back to this side and fill in the ones you haven't done, and then back to the other side. So then when you think you're done, make sure you double check it. You want to make sure that the solder goes all the way around the pad. And you can see this particular one here, it didn't quite go all the way around, so I'm going to go back in, reheat it, add a little more solder. And remember, the tip of your soldering iron has to be run up the pin. You want the solder to follow it up the pin so that it makes a nice cone around each pin. So once again, you want to check it again. You can never check these too many times. Make sure that it is indeed flush on the top before you solder in your next component. So now I'm going to solder in my second socket. So make sure, once again, that all those pins go through all those holes. There's a lot more pins on this particular socket, so you have to be careful. And just check on the bottom to make sure that each pin did indeed go through each of those holes. So I've soldered in the first pin and double checked it to make sure that it is flat against the board. So the next point that I'm going to solder in is on the opposite corner. So when you're soldering on a big component like this, you want to hold it down on the two corners first, just to make sure that it doesn't move when you're soldering in all your other pins. So now that I've soldered it at both corners, I'm going to turn it over and check to make sure that it is still flush on my board. If it's not flush, all I'm going to do is press on it with my thumb on one side and reheat it, just to make sure that I do have it pressed tight up against the board and that it is soldered into place. It's easier to do it now than it is after you've soldered in multiple pins, and then you check and notice it's off a little bit. It's going to be very difficult for you to get it flush against the board later. So I'm just going to go ahead and solder in every other pin and then fill in between them. Okay, so once you've soldered in the socket, the next component you're going to want to solder in is the LED. You'll notice the silk screening has a plus sign, and the LED has a long leg, so the long leg has to go into the hole with the plus sign. Now you want to get it down flush to the board, and you notice this component sits up quite a bit higher than all your other components. So it's going to be a little tricky trying to hold this flush to the board and soldering it in at the same time. So once again, we're just going to solder one leg in and see how that goes. So remember to clean off your tip, add a little bit of solder to the end of the tip, and then come in and we're going to heat up the lead of the LED, heat up the pad of the PC board, and bring in the solder, and try and get it to flow all the way around the pad and then run it up the lead. Now what we're going to do is flip the board over and make sure that it is flush to the board. If it's not, you can always heat that up and just wiggle it around and then run the tip back up the lead again. Now at this point you may not have enough solder on there, so what I'm going to do is I'm going to solder the other lead in, and then I'll come back and add some more solder to the first lead. So once you've got it soldered in, it doesn't hurt to go back and double check, make sure that it is flush with the board. Make sure you haven't got too much solder on there. You might need to go in there and take it off with some solder wick or a solder sucker and try again. One thing you don't want to do is keep heating up the pad, because the pad will eventually delaminate from the board. So be very careful how much heat you're putting on these. So when you're eventually happy with the soldering that you've done, remember you want to cut these to approximately the same height of your resistors. So you don't want to be cutting into the solder. You'd want to be about 1/8 of an inch above the solder. And remember to hold on to them so they don't fly across the room, and try and get both of them to approximately the same height. So I'm now going to go ahead and solder in the remaining LEDs. So don't rush putting in the LEDs. A lot of times I see students take a look at their board and maybe several of these LEDs are a little bit bent or off to one side or something, and what they'll do is they'll come along with their great big fingers and try and straighten them up. Do not do that, because if you try and straighten up an LED that's being soldered in, you're going to end up breaking the pad right off the board. So do not be tempted to move any components around once they've been soldered into place. Okay, so once you're happy with your LEDs, the next component we're going to put in is the capacitors. So make sure you orient them the correct way around. So you can see my plus sign is down here, so that's the longer lead. So I'm going to solder in that capacitor first. And you can see it stands up a little bit higher than my other components. So I'm going to put both capacitors in. And remember, the second capacitor, the positive, is at the top of the board. So the long lead goes in the top. So now I've got my two capacitors in that are going to hold my board up to a specific height. So they're both about the same height. But once again, I'm only going to solder one lead at a time. So what I'm going to do is I'm going to come in with a clean tip. I'm going to add a little bit of solder to my tip. And then I'm going to come in, and please notice that the leads and the pads are fairly close together. So you don't want to get too much solder on these pads because they could short out the capacitor. So very carefully coming in here, heating up the pin and the pad, bring the solder in, and then run the tip up the lead. Now check it to make sure there's no holes around there. Now I can see I need a little bit more solder, so I'm going to reheat it, add a little more solder. So then I'm going to do the same thing with the other capacitor. Now you notice as I'm moving it, it's wiggling around a little bit. So I'm only going to solder one lead in place. Okay, so then what I'm going to do is I'm going to turn the board, and I've got my capacitor in there. So I'm going to put my finger on the capacitor, reheat that pin, and push down hard to make sure that the capacitor is sitting flush with the board. So remember, I've got two capacitors here, so I have to check both capacitors. So the other capacitor, I've only soldered in one lead. I'm going to heat it up and make sure that it is flush with the board. And hold it in place for a little bit longer than you think you need to, just to let the solder cool. And that should hold it in place for you. Then you can come back and solder in the other pin. And then you can fix up any mistakes you made on the first pin. So if it needs a little more solder, you can add that in at this time now. So make sure you inspect it thoroughly. Make sure that it is sitting flush on the board. And then we can trim those leads. So the next component I'm going to solder in is the potentiometer. And keep in mind it has wider tabs at the top of those pins, so it's not going to go all the way in. So in this case, what we want it to do is to sit as flush as possible with the tab. So each pin should be able to sit fairly flush. And when we solder this component into place, once again we're going to solder just one leg first. So clean your tip, add a little bit of solder to the tip, come in and heat up the first pin, bring a little solder in, make sure that it does flow around the pad, and make sure the tip goes up the pin. Once again, we're going to turn the board over to make sure it is flush before we solder in the other two pins. Okay, so once you've soldered in your potentiometer, the last component to go in is going to be that connector. So make sure that the silver part, which is where we're going to put some wires in to power this circuit, is facing the outside of the board. So we should orient it this way. Remember, on the back it's just all plastic, so the wires don't go in that side. Now once again, we're just going to solder one pin in place. Now these pins are a little bit larger than the resistors or the capacitor legs, so it might need a little more heat. And the pad is also a little bit bigger, so it might need a little more solder. So once you've soldered one in place, make sure you lift it up and take a look to see if it is indeed flat with the board. So you may have to reheat it and push your component in to make sure that it is flat with the board. So once you're happy with that, then you can solder in the second pin. So now we've soldered in all the components. There's one thing we want to check, and that's to make sure that we have no shorts in the board. So we're going to do this before we put the ICs in the socket. So the first test I want to do is using the digital multimeter on the ohm setting. And what I've done is I've got the two alligator clips going to two pins that are going to the power supply connector on my printed circuit board. And I want to measure the resistance between the two pins. And you can see right now it's flashing 40, so that's infinity. So that means I do not have a short on my board that's going to affect the battery that I'm going to try and plug into it. So now what I'm going to do is I'm going to plug in a 9-volt battery to this thing. So you can see I have a 9-volt battery clip, and I've connected it to the two screw terminals on my board. Please note the screw terminals are labeled, so on the silk screening, the one towards the LED or closest to the LEDs is labeled GND, and the one closest to the capacitor is labeled VCC. So make sure VCC goes to the red lead and GND goes to the black lead. So the next thing I need to do is to put my ICs in the socket. So make sure that you line up the little dent in the top of your 555 with a little dent on your socket. And be careful when you place these in. We do not want to bend up any of the pins, so it might take a little bit of coercing, and we should be able to slide it right down into the socket. Make sure that none of the legs are sticking out the top. They should all slide straight down. So next we can put in the 4017. So you can see the little notch at the top has to line up with the notch on the socket. And what I do sometimes is I put the IC in on one side and just give it a little push to the one side so that the other side the pins can slide down in, and then give it a little push in to make sure that it does make contact. Once again, make sure all the pins are not sticking out to the side. So once you've done that, you can now find a 9-volt battery. So make sure you line up your 9-volt battery with the battery clip So the small one goes to the large one and the small one goes to the large one. So it just kind of snaps in there, and when you do that, your board should start working. Now mine's has the potentiometer adjusted, looks like it's about midpoint. So if I rotate it counterclockwise, you can see it goes faster. So that's the slowest that mine will go right now. As you can see, it goes from one end to the other end. It would be nice if it went back and forth. So in the rest of the video, I'm going to show you how to modify this board to make a Knight Rider pattern rather than just a light sequencing pattern. So I'm a big fan of Wikipedia, and what we're going to do now is talk about some troubleshooting. So troubleshooting is a form of problem solving often applied to repair failed products or processes on a machine or system. So it's a logical, systematic search for the source of a problem in order to solve it. So what we're going to do is try determining the most likely cause in a process of elimination. So we're eliminating potential causes of a problem. So I'm going to step you through some of the things that I look for when I try to troubleshoot some of these projects. So in order to do any kind of troubleshooting, you really have to understand your schematic, because your schematic is how your circuit is wired up and how it's going to operate for you. So I'm just going to zoom in a little bit here, and what we're going to do is we're going to take a look at our circuit. We've got a 9-volt battery and we have a capacitor. So the purpose of the capacitor is just to filter out any noise on our power line. The next section is for the 555 timer. So you can see it's going to charge up through R11, R12, R13 onto our capacitor, and then it's going to discharge from our capacitor through R13 and R12 to the discharge line. Our output's going to be a square wave on pin 3. So if you want to know how the 555 timer operates, you can go to my YouTube channel, the Darren Holmes. You want to go to the Digital Labs playlist, and it's Digital Lab 9 on multi-vibrators. And in here you can see I've actually simulated the entire operation of the 555's internals in MultiSIM, and I go over it in great detail on how it operates. So having reviewed the 555 timer, we're going to do a few calculations. So we're going to start with the fastest frequency, and that is going to be when R13, or your potentiometer, is set to 0 ohms. So the time high is going to be equal to 0.693 times R11 plus R12 in brackets times C. So this is 0.693 times the 2.2K plus the 10K times the 1 microfarad. And that's going to be equal to 0.00855 seconds. Time low is going to be equal to 0.693 times R12. So it only discharges through R12 times C. So that's going to be equal to 0.0069 seconds. Then the period of the waveform is equal to the time it's high plus the time it's low, and that'll work out to 0.0154 seconds. And then remember, frequency is equal to 1 over the period, so that works out to 64.9 hertz. So next we're going to calculate the slowest frequency. For the slowest frequency, our potentiometer is going to be at its maximum, which is 50K ohms. So this time, the time high is going to be equal to 0.693 times the sum of R11 plus R12 plus R13 times the capacitance. So you can see in the calculation here it's 0.693 times 2.2K plus 10K plus the 50K ohm potentiometer times the 1 microfarad. And you can see here it's going to be equal to 0.043 seconds. Then for the time low, it's going to be equal to 0.693 times R12 plus R13, because now our potentiometer is 50K ohms. and we multiply that by the capacitance, and that's going to work out to 0.042 seconds. So the period's going to come to 0.086 seconds, and the frequency is going to be about 11.6 hertz. The next part of the schematic is the 4017. So we have not used a 4017 before. You'll notice it's got a clock input. It's got some kind of, looks like a master reset and a negative clock pulse going to ground. And then we have these 10 output lines that are connected to our LEDs. So let's take a little look at the data sheet for the 4017. So this is the data sheet for the 4017. It was a fairly old IC, and you can see this data sheet was kind of scanned in, so it's not very clear to read. When you scroll down to the characteristics, you can see the supply voltage for the 4017 is 3 to 18 volts. So that's going to work nicely on a 9-volt battery. When we scroll down to the timing diagram, you can see it's not very clear. There is another IC called the 74HC 4017, which is pin compatible with the 4017. And you can see its data sheet is a little clearer and easier to read. You'll notice in the absolute maximum ratings that this IC is only good for 7 volts, so you can't use it with a 9-volt battery. But when we look at its timing diagram, you can see it's a little bit clearer to see. What I wanted to show you here is we have a clock that comes in, and you can see these are our outputs labeled 0 through 9. So if we start with our output 0 being high, you can see it changes on a positive going transition on our clock pulse here. So it goes from output 0 being high to output 1 being high, and then output 2 being high, all the way down to output 9 being high, and then it repeats the pattern 0, 1, and 2. So I'm going to show you where to find some replacement ICs over on DigiKey, and just to remind you that if you can't find some 4017s, you can use the 74 4017, but you have to use them on a lower voltage. You can't run the 4017 in the 74 series on a 9-volt battery. One last thing I want to mention, if you're trying to get some extra ICs, the 4017, the first time I came here there weren't any in stock. Now they have 51 in stock. This part number is CD4017BE, and if you scroll down to the product attributes, I just wanted to bring to your attention this particular IC operates on 3 to 18 volts. They also make this IC in a 74HC 4017 version. This was to make it more compatible with the 7400 ICs that work on 5 volts. If you scroll down to the product attributes, I want you to note that the voltage supply is only 2 to 6 volts. So if you're planning on using your project with a 9-volt battery, you have to use the 4017, not the 74 4017. I also checked out the stock of the 555 timer, and if you scroll down to the product attributes for the 555 timer, you can see it can operate on 1.5 to 15 volts. So what I'm going to do now is zoom out a little bit, and I'm going to run the simulation. And if your battery reads 0 volts, they just re-ghosted all our machines, and for some reason the 9-volt battery wasn't working. All you need to do is come up to the Simulate menu item, click on it, go to Analysis and Simulation, and in Interactive Simulation we need to have the analysis parameters showing, and what we need to do is change our initial conditions. So if you click on that, we have several items we can choose from. We need to choose user defined, and then we're going to click on save. So now when you run your simulation, we should have 9 volts on the battery. And then it should run through our sequence. So you can see it's slowly advancing each of those LEDs. And then when it gets to the last LED, it should come back to the first one and continue on. So now we have an understanding of how our circuit works. We can go back to our board and find out what our problems are with it. So usually in my labs I have anywhere from 20 to 30 students working on these projects. So they're going to come up to me and they're going to say my project's not working. So I'm going to ask a few questions before we get started. The first one I'm going to ask them is, does it do anything? So that's an important question, because if just one light comes on, it means our 4017 is working and the IC is getting power. Now, if the light isn't blinking or advancing to the next position, then that means the 555 is not working. But let's say they bring it up to me and nothing works. So where do I start troubleshooting these? So what I'm going to do is I'm going to take it and I'm going to do a visual inspection. First thing I'm going to do is check to make sure that this red lead does go to the terminal labeled VCC and the black lead goes to the terminal labeled ground. That's the first check I'm going to do. Then I'm going to ask them the voltage on their battery. You'd be surprised how many people bring up a 9-volt battery and it only measures maybe 2 or 3 volts. That's just not going to work. A 9-volt battery needs to be at least 7 volts or above. Then the next thing I'm going to do is I'm going to check the ICs. Right, so we have these little notches in the top of the IC to indicate which way around the IC goes. So I'm going to check both ICs and make sure that the notches are in the correct way. The next thing I'm going to do is check the resistors. Most of them should be 1K, so it should start with a brown. And then over here we have our resistors for the timing circuit. If you put them in wrong, it's just going to change the timing, right? But at the top should be the 2.2K followed underneath by the 10K. So one of the things I'm going to check for when I'm doing my visual inspection of the board is I'm actually going to run my finger over some of the parts and make sure that they don't wiggle. Because if any of the parts wiggle, what it means is we either didn't solder them in, or we've soldered them in, tried to readjust and knock the pad off the board, in which case it won't make contact. Either way, that has to be repaired somehow. A lot of times we end up putting in another LED and bending the lead over onto the trace. So if you're going to solder something to the trace, you're actually going to have to scrape off that green coating till you get down to the bare track, then put your new component in, bend the leg over, and solder it directly to the trace. The next thing I'm going to do is check the LEDs and make sure they're in the right way around. Now a lot of people tell me, well, I've cut the leads off these LEDs and now I can't see which lead's the longer lead or the shorter lead. So if you come back to your instructions, you can see they have the diagram for the LED, and on here we have the anodes, the positive side, the cathodes, the negative side, and you notice the negative side has a little flat spot on it. So this flat spot corresponds to the cathode. So you can see on our connector terminals, the bottom one here is labeled ground. So that's going to be closest to the cathode on the LEDs. So if we flip our board over and follow the trace down, we can see it goes down to these connectors right at the bottom of the board. So flipping the board back over again, if we look at the bottoms of these LEDs, we should see a little flat spot. So all our workbenches have these lighted magnifiers, so we should be using those to check out our circuit board. So if you adjust these to just the correct angle, you will actually be able to see through the magnifier that these are all the little flat spots on the LEDs. So make sure all the flat spots are pointing towards the bottom of the board. If they're put in backwards, the LEDs will not operate. So then once I've done those checks, the next thing I'm going to do is actually take the ICs out of the sockets. So I'm going to use a small flat bladed screwdriver, and you just pry underneath from one end and then pry underneath from the other end. And we're trying to pry the IC out of the socket without bending all the legs up. Now I do this for two reasons. The first reason is I want to check all the legs and make sure that you haven't pushed it in and bent one of the legs up underneath. A lot of times this will happen and then the IC will not work. The other thing is I check the socket to make sure that each of the holes has something shiny in it, because that's the shiny pin that's going to go down into your board and make electrical connection. A lot of times students will push the socket into the board and the pin will just pop out and they'll just continue on. So it is possible to take a pin out of another board and insert it in here. So looking at the bottom of the board, there's not too many things that can go wrong, but I will check all the pins on the socket to make sure that they are all present. A lot of times students will try and put these sockets in and the pin will bend up underneath, and what they'll do is they'll just solder in a little blob of solder on the pad to make it look good, but if you can't feel the pin poking through, then it didn't get through. Now the next thing I'm going to do is actually take a look at the board and see if there's any flux. So some of these pins here we have an excess amount of flux. So what is flux? So flux is in the core of the solder, and flux helps solder to flow, and it also helps to clean the connections. So the connections are copper pads. So what gets on the copper pads is an oxidized copper, so copper oxide. So the flux will flow onto the pad and lift the copper oxide up. So any of these connections have the possibility of some impurities like copper oxide coming out into the flux. And if it flows between two pins, we could end up with either a small resistance or a short caused by just the flux. So what I'd do now is I would tell the students to actually clean the board. So in the lab I mix up a product called BioClean, and it comes in like a 1-gallon jug. It's for industrial use. So you can see this product is made by Kester. Its product number is 5768, called BioClean, and it's a concentrate. So I do have to dilute it before I give it to the students. The other option is to use a spray cleaner. This is by MG Chemicals and it's called Heavy Duty Flux Remover. And the thing to keep in mind, it says aggressively dissolves all types of flux, including burnt-on flux. But right here it says harmful to some plastics. So when you're looking at your printed circuit board, those IC sockets are plastic, your screw terminal's plastic, the casing on the LEDs are plastic. So there's a lot of plastic on these printed circuit boards. So when you're cleaning the bottom of it, you want to make sure that you do not spray enough on here that it goes through to the top side and starts eating into your plastic components. So what I like to do is actually place my board on a piece of paper towel, and I'll bring the nozzle in and I'll spray my board on an angle. Now you're trying not to get this stuff on your fingers. It does squirt out fairly aggressively. So you want to get over all the pins and make sure your table isn't covered in a plastic material. And if it's really baked on there, you might want to use a little bristle brush and just kind of scrape over there and get rid of anything that's on there. And then just dry it off on your paper towel. So I like using the BioClean in a lab room because it doesn't give off the strong odor like the heavy duty flux remover that you spray on does. So if you've done all that and the project still doesn't work, then you may want to try swapping out the two ICs. CMOS ICs are static sensitive, so the 4017 can give you some problems depending on how dry the air is when you are handling it. So keep that in mind. And if all that doesn't work, then it's time to break out the voltmeter. So on the next step, what I'll have the students do is break out the voltmeter and check the voltage between pin 8 and pin 16. That should be the 9 volts on the battery. And then we'll check between pin 1 and pin 8 to see if power is getting to the 555. Now if both ICs are being powered, then the next thing we're going to do is hook up the oscilloscope and check the output on pin 3. So the output on pin 3 should be a square wave. So in order to check the output of pin 3 of the 555, we need to power up our circuit. We need the ground clip for the oscilloscope hooked up to a ground point on our board. So a good point would be to clip it onto a cathode of one of the LEDs. And then with the probe we can just touch it to pin 3 of the 555 and check our oscilloscope. So checking out my oscilloscope screen, you can see I have a square waveform on here and it's running at about 10 Hertz, so it's pretty slow. But that's what we're expecting to see coming out of the 555 timer. So once we've done those checks, there's only one last thing we can do, and that's to disconnect our power supply, take out our ICs, and then check the connections between each of the pins, just like we did when we originally checked the board out. Hopefully by then we'll have found an error somewhere. So hopefully once you've completed my list of troubleshooting techniques, you'll be able to get your board going. So earlier on I took you to the ABRA website and we looked up the AK75 LED Ripple Flash Kit. And when we scrolled down and looked in the description, it says we can hack the board to create a Knight Rider circuit. Okay, so for those of you who are not familiar with Knight Rider, just go over to YouTube and type in the Knight Rider theme and play the little video. So this was a pretty cool TV program when it came out, and we can see on the front of the car we have this little Knight Rider pattern coming up. So this is what we're going to hack our board to accomplish. So what is hacking? I went over to Wikipedia, and under hacking they have hacking of consumer electronics. And the hacking of consumer electronics is an increasingly common practice which users perform in order to customize and modify the devices beyond what is typically possible. So if I was building a Knight Rider circuit, and I have built a few of these in the past, what I would do is, coming out of the 4017, I would go through a small signal diode. So here I'm using 1N4148. You could also use a 914. Just a small signal diode. They're glass. They look kind of nice. And what I would do is I would have the first one going to the first LED, and the second one going to the second LED, third to the third, fourth to the fourth, fifth to the fifth, and sixth to the sixth. And then on the seventh output, I would now connect that through a diode to D5. So instead of going R6 and then R7 to D7, it now goes R7 to D5. So then I would continue that sequence on, so I go from R8 all the way up to D4, and then R9 would come up to D3, and then R10 would kind of follow up here to D2, and then the pattern would repeat again at D1. So I'm going to include these simulation files at the bottom under the video so you can run them if you want. If you get a simulation error, it's going to come up with a convergence assistance. Just say no, and then go into your simulate, analysis, and simulation, and interactive simulation, analysis options. Use the custom settings and customize. So just reduce your ABS TOL, your VN TOL, your REL TOL. I just made a small change to the ABS TOL. I'll show you what that looks like. So what I did was I came up here to simulate, and I came down here to analysis and simulation, and under interactive simulation I went to the analysis options, and then I came down here to use custom settings, and then I clicked on customize. So you can see in here I have the ABS TOL. I clicked on it and I changed it to 1E minus 010 amperes. And that seemed to solve the problem for me. Okay, so here's the problem with doing this modification on the board as it was supplied to us. The first thing is we have to remove 10 resistors and replace them with 10 diodes. So that's going to give us an opportunity to actually damage some of the pads on our board. The other thing we have to do is kind of do some kind of crisscrossing here. So we're going to take out 4 diodes, and now they're not going to be centered on the board. And we have to run 4 jumper wires and somehow tack them across our board. The other thing we need to do is add a current limiting resistor to each of these LEDs. So in order to do that, we're going to end up cutting one of the traces and then trying to tack a resistor on. So that's going to be a lot of work. So I've come up with an alternative way of accomplishing this modification. So in this modification, what we're actually going to do is take off the first 2 LEDs and the second 2 LEDs. So that's going to center our LEDs on our board, and our board's still going to look pretty nice. I still have to take off 4 LEDs because we're not going to be using them. Instead of using diodes, I'm just going to leave in the 1K ohm resistors. So that eliminates the need to cut a trace and put in a 1K ohm current limiting resistors on these LEDs. What we're going to do is we're actually going to cross the wires at the 2 ends of the board, so I don't have 4 wires crossing each other. So it's going to be a little neater when I do this modification. So I'm just going to zoom in a little bit here and talk about this modification. So what we've got is a 1K ohm resistor going to a LED, which is going back to ground. So if we're working this on 9 volts, then a 1K current limiting resistor is a good choice. Now what we've got is a case here where we've got 2 resistors going to 1 LED. So what we're going to end up here with is a 1K ohm in series with a 1K ohm coming back to our other output. So one output's going to be plus 9 volts, the other output's going to be 0 volts. So what that says is we've got 2 1K ohm resistors. What will be the voltage here? So what we're going to do is just think about it as the voltage divider circuit. So we should get approximately half of our 9 volts, which is 4.5 volts. So 4.5 volts should be enough to run an LED. Now remember, part of the current is going to come in through R2, part of the current is going to go through R4, and part of the current is going to go through D4. So having all those currents running through there, we're going to end up with a voltage of 1.77 volts. So that's perfectly okay to run our LED. Most LEDs need about 1.4 volts to turn on. So instead of using a diode to make sure current only flows in one direction to the LED, we've now got current flowing backwards through the second resistor and the second resistor, the value of that resistor is big enough that we still have voltage left over to run our LED. So I'm going to go ahead and run the simulation for you. So what's going to happen is I'm going to run the simulation and D5 comes on. And then you can see we're going to D4, then D3, and then D4, and then D5, then D6, then D7, then D8, and then we should come back to D7. So you're going to get a strange startup, but because this is going to be running at about 10 Hertz, you're probably not going to notice it. So what's happening here? The first output comes on first, turning on D5. Then the second output comes on, turning on D4. Then the third output turns on D3 all by itself. And then the next output comes on and turns on D4. And then it should continue on. So this is the method that I'm going to use to do the modification to my board to get a Knight Rider pattern running on it. So in order to show you the connections, what I've done is I've taken a picture of the bottom of the board and imported it into a paint program. So I'm just going to go in and view this. So I'm going to view this full screen. So you can see what I'm saying here is the outer two LEDs on each end of the board are going to be removed, and they're going to be replaced with 4 jumper wires. So what I'm going to do is I'm going to install the shorter jumper wires first, because if I install the longer wires first, then when I solder in the shorter wires, the soldering iron is going to heat up this pad and the wire, and I could melt the insulation on this other wire. So in order to avoid that, I'm going to put in the shorter jumper wires first, and then I'm going to put in the longer jumper wires. Now keep in mind, when you're soldering these in, these holes here are actually going to have LEDs in them. So what we're going to do is we're going to put the wire into the empty hole and then kind of solder that into place, and then we're going to tack the other end up against the lead for the LEDs that are already in place. So I'm going to include this photo in the notes below the video so that you can download it, print it out, so you can see what you're supposed to be doing when you do this modification on your board. So before you start doing any modifications, make sure that your board is functioning properly. Then the next thing I did was print out a copy of the picture that I modified to show what I'm going to be doing to do this modification. So I need to take out the 2 LEDs on the 2 edges of the board, and then I need to put in these jumper wires. So I'm taking out 4 LEDs and then adding 4 jumper wires. Now you can see I've already pre-stripped my jumper wires. I haven't stripped them back very far, and I've measured against my board approximately the length I want them to be. So to desolder those 4 LEDs, I'm going to desolder 2 of them with the solder pump, and I'm going to do the other 2 with the solder wick, just to show you the difference between them. So remember, the solder pump, usually one end you have to push it in and you'll hear it go click, and then this end here actually has a little hole in it, so you want to get that over the pin and press the button, and it should suck the solder up. Now this is going to be kind of difficult to do if you don't use a vise or something. So what we need to do is actually heat up the pin and melt the solder, bring in the solder sucker, put it right over top, and release it. And if you do that correctly, it should remove all the solder from the pin, the pad, and you should be able to see a hole right the way around it. Now if you've done that correctly, the LED should wobble. So if it does wobble, then you're free to just kind of slide it out. So I'm going to try and do these 2 with the desolder braid. The desolder braid has some flux in it. So what we need to do is to actually get a little bit of solder on our tip, because we want the heat to transfer to our desoldering braid. So I heat up the braid and just bring it close to the pin, and the braid should suck the solder right off. So now you've got a piece of braid with solder in it. So what we need to do is actually cut that piece off, because if we try and drag that along our board, as it cools, it will stick to other pads. So cut the piece off that has the solder in it, and then we can go heat it up again and do the same thing for the second pin. So you can see my LED wobbles now, but it's still not totally desoldered. So you're going to have to go back and reheat it, and hopefully it will just slide out. Using a vise to hold your board is going to help you. So what I'm going to do now is come in with a clean tip, add a little bit of solder to it, and what I want to do is heat up that pin and add a little bit of solder. So in order to make the second solder connection, I want to pull the wire out a little bit, because I'm actually soldering between the pad and the jumper wire. So I need to be very careful when I'm doing that. So once again, I'm going to come in with a clean tip, add a little bit of solder, and I need to get in here and heat up the wire and the pad and bring in a little bit more solder. So one end of your jumper wire is going to solder flat to the pin, right? So it's just going to be tacked on the side of it. Be careful when you're holding it down with your fingernail, right? It's going to get hot, so use your fingernail. Make sure you don't push too hard on the insulation, because it's going to get hot and you will mark it. On the other end, it's going to be lifted up off the board a little bit, because I'm trying to get the solder to flow from the pad onto the jumper wire. So it will be sticking a little bit up off the board. So now I'm going to do the other jumper wire. So once again, I'm going to come in with a clean tip. I need to put a little bit of solder on it. I need to hold that little wire still, and I need to heat up the jumper wire. I need to heat up the pin. I need to bring in some extra solder. So once again, I have to lift this little jumper wire out of the hole a little bit so I can come in here and put some solder on there. So once again, I come in with a clean tip, add a little bit of solder, heat up the pad and the wire, bring in some extra solder, and you're trying to make a nice solder joint here. Okay, so I've got the first longer jumper in, and it takes a while to bend the wire to the correct shape, because you want the wire touching the pin. You don't want to have to be holding it down with any kind of force. So you're going to need to hold this little wire into position. We don't want to hold it too tight, but we do want it to make contact. We need to bring in a clean tip with a little bit of solder on it. And we're trying to heat up the jumper wire, the pin, the pad, add a little solder in. So then once again, I have to lift the end that's going into the hole. I don't want it coming out of the hole, but I do want it out a little bit so that I've got an area to solder to. So once again, I come in with a clean tip, add a little bit of solder, and I'm trying to heat the wire, the pad, bring a little bit more solder in. So now I want to tack in my fourth jumper wire. Then I have to lift it out at this end where it goes into the hole. Okay, now I need to solder in my last connection. So I'm going to bring in a clean tip, add a little bit of solder, heat up the wire and the pad, bring in a little more solder. So you can see I've finished the modification. Modifications never look very good, especially when you're looking at the bottom of the board. But when you flip it over to the top, it barely looks like there was any modification done on it at all. So now hopefully when we plug in our battery, our project should work. So this brings us to the end of our video for assembling the AK75 LED ripple kit, and we've done a pretty nice modification, I think. So please don't forget to subscribe, and thank you very much for watching.